Howdy, everybody. My name is Charles Noren. Today I'm going to be talking about a project I've been working on for the last couple months to help support the in-space assembly efforts here at NASA's Langley Research Center. And the topic of my talk today is about environmental mapping using scanning LiDARs. As you all know, my mentor is the fabulous Dr. Ned Allin. A little bit of an introduction about me if you don't know me already. I come from Houston, Texas. I went to undergraduate at Texas A&M University, but now I'm going to be going to Carnegie Mellon for a PhD in robotics starting next month. So I'm a negative 1 month PhD in robotics student at Carnegie Mellon. I have no advisor and I don't know my topic, so I'm kind of lost on the sea of PhD life right now. And over the next couple of months, we'll end up hopefully coalescing into some sort of direction. So today, I'm going to talk about one of the particular aspects that we're working on here. It actually ends up slotting in before a lot of the work that we're currently doing, and it's really about robotic perception. We want to know more about our environment. We want to understand about how the actual robots end up being able to react to their environment and how they can end up determining what they want to do and do this intelligently. So, in my opinion, robotic perception really underpins almost all autonomous operations. If you don't know where you are, if you don't know where other things are in your environment, it's really hard to operate safely and effectively around them. Our friends over at the ESA really had a cool definition of perception that I've had to massage to get it to fit onto this chart. But their definition describes the fact that robots are different from simple machines because they are able to adapt to changes in their environment, right? It's not just simply doing something, it's being knowledgeable about that something. And so being able to understand your surrounding environment, that's one of the ways you are able to change to it because you understand and are able to react to changes in that environment. Additionally, they describe the fact that we have to be able to implement some sort of control or actuation in order to be able to actually see or cause some sort of effect in our environment. And that's how we can really describe whether or not this perception has been effective, right? If we perform a correct action, then hopefully we have, seen the correct representation of the world. It's like whenever we do something, whenever we have some sort of misjudgment in distance, or maybe you get tricked by an optical illusion. We don't want robots to do that, and so we want to be very, very careful in all of the actions that we commit. So what I've been tasked with is this idea of mapping, right? And this is building an environment from the robot's perspective, in effect. Now, if you all are familiar with Jeremy's work, he has almost a little bit of a different style of mapping, but we end up utilizing these maps in a somewhat similar way. For him, it's trying to be able to build a landing area that's safe to be able to land on. For me, it's trying to be able to operate in the ISA context, being able to move trusses or being able to understand the physics of the environment a little bit better. So what we're hoping to do with all of this work is to have a good understanding of that environment so that we can more accurately define our relationship to that environment and be able to better plan and perform the appropriate actions we want to occur. So this is a quick summary of the problem statement. Basically, we want to have a robotic capability. In other words, we want the robot to be able to do something that, given some sort of search area that's predefined, allows us to be able to map the environment in that specified area, right? And so the solution that I am proposing is a mobile manipulator. In this case, it's actually going to be a static manipulator. It allows us to utilize a LiDAR to scan a target of interest. And the way that we're going to do that is by utilizing a UR10 arm with a scanning LiDAR. And we'll control it in ROS in order to build a picture that you can see up here. And this is actually a live demonstration, so the arm behind me is in fact scanning. And we'll talk a little bit more about it when we get to the results section, but hopefully over the course of this demo, this won't be too distracting, but you'll actually get to watch the scan aggregate and build up a point cloud in real time. So our scanning strategy is that this LiDAR, it's a light reflection device, is going to provide distance information in a polar coordinate frame from the ego frame of the LiDAR, and that will allow us to steadily build up what we're trying to do. In other words, if you see this kind of cartoonish representation of the LiDAR, from the side view and from the top view, whenever the LiDAR is active and scanning, we should start to get information that looks like this, right? So the problem being that since we want 3D objects, we're not looking at paper or some flat, object from the side, we're going to need to know more information about the target of interest other than the fact that we have one scan, right? It's like looking through a set of blinds, or if you're out at sea or something like that and you can only see part of a ship from a lighthouse, right? You need to see able the whole thing. So what we end up doing is trying to aggregate a collection of scans. So Matt here, I caught a scan of him yesterday, and it kind of shows how this whole process works. But instead of using Matt, we're going to use the table, right? So we're going to start scanning. We've ended up building out this point cloud. This is actually Matt. The top of his head is here. You can see his arms. He's working on something, probably coding. And you can see that we've kind of built this 3D representation of Matt in the simulation environment. And whenever we get this kind of scan complete notification from one of the logic units on board, then we'll know that we've kind of captured our environment in its entirety. So for what we're trying to do, we have the robotic arm, as you see here. It's going to start by initializing some sort of planar data that you guys saw at the beginning, and then it's going to sweep through a set of angles. That angular sweep is going to track the information until it gets to the ending angle that we're looking for. And if we're looking for, say, this small quad rotor, what we hope to then be able to do is take that 3D scan and then implement it somewhere in like a simulation, like the attractor sim, or maybe put it into the ISA context so that you can see it in Gazebo, something like that. So in this instance, one thing to really note is that we're really looking at the 3D representation, so we wouldn't have a motion pattern, and for us, that object is static. In other words, we can be very slow in our scanning because we know where it is, and we don't have to worry about it moving on us directly, which can happen in different environments. So like I said, Jeremy's environment is very dynamic. So that's our scanning strategy. Looking at the hardware overview, in other words, how do we achieve this scanning strategy, we had to really have two choices. We have the UR3 arm, and we have the UR10 arm. After looking at what we want to do, we want to achieve this kind of configuration. We realized that the berm, what I call the berm, the edge of this table, is extremely hard to see with the reach that we have on the UR3 arm. So we decided to evolve to the larger UR10 arm instead. So we decided to pick this UR10 arm because it meets our preferred scanning strategy. And we had to pick a certain scanning type. There's a lot of different choices, whether or not we were going to use a point cloud camera, whether we were going to use a flash LiDAR, or whether we were going to use a scanning LiDAR. And looking at how the scans are being aggregated and the tools that I had available with me in the time that I had to develop, I decided that the scanning LiDAR is going to be the best for the time I have to develop. But in the future, there might be a better sensor, and I'll talk about this towards the end of the talk, that would be more useful in actually trying to map out this table. And comparing between the two that we have on hand that we know fit within our architecture, this URG-04LX seems to be a more built for interior environments, looking at this kind of close range. It actually has a closer minimum range. So we ended up choosing to go with this URG-04LX, which we kind of consider that interior LiDAR, versus the UTM-30LX, which you guys see on the hog on the picture on the right there. For a software overview, I'm actually using the ARM architecture that Sharif and Walter have really start defining. And what we're trying to do is we're trying to build capabilities into that architecture directly, right? So the architecture really contains all the libraries, all of the ROS packages, everything that we need to do to be able to interact with our arms and our sensors. And because we're just adding to this particular architecture, we can work on any arm, we can work on any LiDAR, because it's built on kind of this operating system we call ROS. It's really actually just a robotics middleware directly, and we utilize that as kind of the platform to help spur growth. And what we're trying to do is add these particular four capabilities to this entire architecture. We want to be able to determine the scan area. We want to be able to scan information and then aggregate all of that into this larger point cloud that contains everything. And then we want to be able to perform some sort of analysis on it and then hopefully publish that out to some receiver, whether that's another arm or another node, or even within the same robotics computing system, maybe some sort of a real-time analysis node. It doesn't really matter from this particular information, from where I am currently in the pipeline development, but we want to be able to provide that. And what I've managed to do is really get that publication out and get that aggregation complete, but haven't really managed to get to the scan informational analysis side, so what tools do we want to use with it, and kind of from an earlier technicality utilizing our requirements, we are kind of getting away with the scan area determination because we know it prior to this, but a more intelligent operation would require us to be able to determine that scan area. So the ARM architecture that I end up changing is I've gone in and I've listed out everything that I've added into ARM with the help of Matt, who's really been a big push on the AR robot, and then Sharif, who's not currently here, who really helped out with the AR demo class. So both of those guys deserve a ton of credit because of how much work they did. But this is all the different pieces that we've added to ARM. And knowing that these are the pieces, this is how they all fit together to communicate. So the beginning starts at the topography demo. I start that up first. We load up some mission parameters, what that search area looks like, what the scan resolution we want is. And then we say, pass these to some scan angle definer, which allows us to determine the sweep angle for one of the joints to sweep through in order to scan the entire area. Once we've done that, and the scan angle definer has gone through and determined those sweep areas, it sends back a list of scan angles to the robot so that it can start to move through all of those different actions. Once the robot receives the list of scan angles, it passes it forward in a proceed command to the UR arm and the LiDAR. The URG node is the LiDAR, which moves the arm to the position that I want and starts to scan with the LiDAR. After that, that LiDAR node pushes the laser transform and the LiDAR position to an aggregator in order to aggregate the system. And we go back to the beginning with the topography demo, which allows for us to control the flow of the entire process. What we then do is we cycle through this entire loop until all the scan angles have been moved through. So in other words, we're basically doing the same action over and over and over again in order to get a better understanding of our environment. It's what robotics are good at. So the first thing we did is to develop this all in simulation in order to basically try to get a good understanding of how things work, right? Try to be safe in our development process. We simulated everything in Gazebo directly, which is one of the components of the ARM architecture. And what I can do is put into that actual Gazebo simulation some sort of scanned object, the UR10 arm and the stand, and a simulated LiDAR that doesn't actually represent the Kuyo due to some interesting physics as well as some of the specifications that we can have, but allows us to go through the action of scanning. And then what we can do is use that information and those simulated objects to actually test the scanning pipeline, which is what I am responsible for this particular internship. So the pros are that we have this ability to do safer testing and we can get this fast development. As you can tell, this can take a long time if we want a really high resolution scan. Some of the cons are is that that LiDAR doesn't behave like we expect it to do exactly. And I'll talk about why in a second. And that some of the oversimplifications to the environment itself can cause artifacts or kind of emergent behaviors that I wouldn't have expected originally. And I won't expect on this arm. So this is a quick video of the simulation. I promise you it is moving. It's very slow. But what you can see is that there's a red line that is slowly aggregating point clouds onto the plane on this right-hand screen. This is actually the RViz. That's what you see up here, but for the simulation directly. So what's happening is we're slowly scanning through this entire area. And utilizing the simulation, what we can see is we get a fairly good scan of what we expect the table to look like. It looks fairly flat. The actual error that I simulate into the LiDAR is basically a standard deviation of 1 centimeter, 2 centimeters. So what ends up happening is this actual scan that we show here does reflect the simulated variance that we expect to see in the actual sensor itself. And going through these different simulation results, we managed to actually tentatively confirm the pipeline and all these different aspects that allow us to then develop on the actual arm. Which leads us to some of the hardware in the loop testing, which you're actually seeing going on behind me. All the hardware in the loop testing that you're going to see here in this presentation are talking about this 3DOF sim table. That's a big initiative that we're having currently with the inertial transfer side. And what we're trying to do is really understand the surface of the table so that we can work together as an inertial transfer team to better understand what the physics are on that table, to have a better understanding of launching or how those robots are going to have to work together in order to actually achieve that inertial transfer. And so using the hardware that was listed here, I tried a bunch of different scans. And some of these scans, while they could take a while to line up, really end up having a great resolution. And as we'll see in the next slide, so the arm will actually scan through directly, and it ends up subtending a set angle, and ends up going through the entire rotation around wrist joint 1. And after this scan motion, ends up going it ends up actually aggregating the entire table together. There seemed to be a bit of a stutter in the video there. It actually does look continuous, as why it's kind of hard to notice it on the arm behind me as it's scanning through. But that actual action is that's an actual representation of what we're trying to do directly. So the first test that I did was on the table behind me without the cloth on top of it. And we did confirm the pipeline flow, the control and safety systems, that data aggregation. But we'll notice that there's some interesting artifacts going on the table. Like, this doesn't look like a table like you would expect. I would expect the table to be square. Additionally, we're seeming to miss important components of it, like the berm and things like that. And what we find out is that the actual table itself is causing some interference with how the LiDAR is scanning. You'll notice that there are certain types of features that are very observant, like the AI logos in the corner, but things like the planet actually end up making a big divot, basically like a hole in the middle of the table. And so there seems to be some interference coming from the actual table itself. So by adding a felt cloth on top of it, we hope to try to create a flat surface and test the pipeline and verify its capabilities. And that's what we do see. We actually do see a really flat surface. This is the table scan directly. So the scan is getting within a centimeter of accuracy to try to determine the height of the table itself. And with that felt scan, we actually do verify tentatively the pipeline that we're hoping to go through. So some quick conclusions. The scanning pipeline does allow for planar surface scanning, and that, as you guys saw on the last slide, the properties of the scanned object do really affect what we're supposed to see. So we might have to have a different autonomous behavior if we know that the object could be difficult in the future. We know that an intelligent scanning strategy may decrease time of operation. As you see, we've been running through this scan as it slowly fades to black for the purpose of this demo. So this will probably go for about 35 minutes to get the full scan. And if I try to decrease the actual subtending of the angle, it takes longer time. So the question then becomes, how much resolution do we need on the table, and is there a better way of actually scanning? And I think that there is. Additionally, that kind of leads into this fourth one, how we need to know how much resolution we need. Jeremy and I were talking about this yesterday, and it says, for motion planning, you may need a very fine map, or you may need a very coarse map, depending on what you're trying to move through your environment. For us, that ends up meaning that the scanned environment timing, so how long it takes for us to complete one of these scans, is directly correlated to the resolution. And there's a host of issues with the LiDAR simulation and the ROS drivers for it that need to be addressed. I've really gone through and tried to document all of them that I've seen, but there are definitely mitigation strategies that I've caused that need to be put in a more professional, completed way rather than just notes on a GitHub. Maybe we have to address some of these directly. And some of the extensions of future work, we hope to see some more intelligent scan resolution and scan angle definer behaviors. And hopefully we can start to take that and then move into these additive capabilities, right? We want to then build out being able to select a scan area for the target. We want to be able to address that oddity, those artifacting that we see with the table and not have to use the cloth directly. We want to be able to modify the pipeline so that we can use ROS services instead of having this kind of yelling match between the different parameter servers. And we want to try to build applications that really allow us to utilize this point cloud data, one of the points that I was talking about earlier that I hadn't gotten to yet. And then hopefully some of the larger goals is that we can then take maybe some different types of sensors, like a flash LiDAR that will capture the entire scene at one time and integrate that, or add more intelligence or autonomy with multi-agent work to try to get a better understanding of the scene and the environment that it exists in. So some quick acknowledgments. I wanted to thank Danette for being an amazing mentor and guide and help and teacher throughout this entire process. Both Ben and Jamie deserve shout-outs for being my inertial transfer teammates here, who have really given me a good idea of what I need to do to fit into the pipeline. The entire AMA group here has really given me a lot of help, whether that's for C++ or developing a lot of the work or helping me with the strategy moving forward. Payton never gets enough credit for all the hard work she does, so definitely give her a round of applause for all the help she's done building the creative content and, as you see, filming here today. And then Carol, Nicole, and Eric really at the branch level help make this process go smoothly. And Christine, Patricia, and Valerie, who it's good to see you guys here today, for being awesome internship coordinators. Oh, and this date. This is a really cool date feature. Whoever decided to make the date automatically update with the day that you're giving the presentation is brilliant, because I always forget to change it. So that person deserves a round of applause as well. and I'll take any questions at this time. So the voxels that are in the visualization are a 1 centimeter voxel. So the cube, each cube is 1 centimeter by 1 centimeter by 1 centimeter. Currently, I do not account for them, but that should definitely be an extension, is to account for some of the error. Currently, we're relying on the precision of the UR10 to accurately report what it expects to see at the state. It looked like there is some scanning behavior where the wrist joint would move back and forth between positions. And I believe, from what I can see, that that's just an artifact of the video. I don't observe that particular behavior on the arm right now, but that's probably a function of my computer that's trying to render the video in real time. So I don't see that behavior, but I can't confirm or deny that it exists.